guys, welcome back to Learn the Concept, session 4. So today we will be talking about skewness and kurtosis. So we have already talked about measures of central tendency and dispersion, which are ways to represent the distribution of the data. Uh, Complementing that are also the concepts of skewness and kurtosis. So we will be talking about that, right? So what is skewness, right? So skewness is basically a concept or a metric that tells us whether the distribution is symmetrical or is it tilted in certain direction, right? So, for example, if you recall what is a normal distribution, right? Normal distribution is a bell-shaped curve which is symmetrical around the center, right? So there is a symmetry between the left hand side and the right hand side of a normal distribution. There are equal number of observations on both the sides. However, in real life, it might be possible that there are situations where the data is skewed, right? For example, the number of students who are good at both academics as well as sports might be might be concentrated in the cities of the country rather than the villages, right? So if we plot that kind of a distribution, it might be skewed, right? So it tells us whether a distribution is symmetrical or tilted in one direction. There are two types of, actually three types of skewness, which is zero skewness or symmetric, where we are saying that mean is equal to median is equal to mode. Example is the heights of the people in a population is kind of symmetric, right? Or has zero skewness. Then we have positive skewness or right skew. Here, the mean is greater than the median, right? So mean is greater than the median, which means that there are extreme high values, right, on in the distribution, which is skewing the mean or which is pulling the mean towards the right hand side. And that is why mean is greater than median. The tail extends to the right. So examples of this are income distribution and sales growth, right? Uh, Income distribution and sales growth, meaning, so why is income distribution a right skewed distribution? Because in most countries, there will be very few people who have very high wealth, right? So hence, it is right skewed, right? And sales growth also is kind of a right skewed distribution, because as you can imagine that there will be very few quarters in which the sales growth would be very high. In all other quarters, it would be kind of tempered. So that is what, right? We have a negative skewness or the left skewed where the mean is less than median. There are extreme negative values in that, and it pulls the mean towards the left hand side, right? So the example is exam scores when most students score high marks. So now we will see in R certain examples of how the distribution looks in case it is skewed, right? So I'm just installing a package called Moments because it is important to compute the skewness. So basically, there are certain functions in R called skewness and kurtosis, which are a part of this library Moments. So in case you do not have the Moments library installed, you could just run this command, which is install.packages moments, right? I have already done this, so I will for now comment it. I just bring in the library moments by calling it set.sheet, as we have talked about in previous videos as well. It is just to ensure the replicability of randomly generated numbers. Now, for symmetric data uh, and right skewed, left skewed data, I am using certain distributions, which I already know. For example, the normal distribution is going to be symmetric here. So I'm just creating that symmetric data. Similarly, I'm creating certain right skewed and left skewed data. This is synthetic data just for the purpose of explaining. So I already know that an exponential distribution with 1,000 observations would be right skewed, and similarly the negative of it would be left skewed, right? I'm just generating this data, so do not read too much into the syntax here. It is just for explaining how the distribution basically looks. Now we just compute the skewness of each of these data sets and print it out, right? So we can see that the symmetric skewness, so basically the skewness of the symmetric data here is close to zero. The the skewness of the right skewed data is positive, right? So whenever the skewness is positive, we say that the data is positively skewed, and similarly the skewness of the uh, left skewed data is negative, right? Whenever the skewness is negative, we say that the data is left skewed. Now we just plot these data sets and we see how these looks, right? So symmetric data. As expected, it is symmetric, right? If we see here, it is symmetric from the middle. So there are equal number of values before the mean and equal number of values after the mean as well. Then there is a right skewed data which has a long tail on the right hand side. So right. So when I say long tail, we look at this, right? So on the right hand side of the graph, there are a lot of values with very less frequency. So this is a right skewed data with a long right tail. The mean obviously is would be somewhere on the left hand side here because that is where majority of the values. Sorry, the mean would be somewhere on the right hand side here because that is where majority of the high values live. But the median would be somewhere in the middle, right? So the mean is greater than median in this case, and hence it's a right skewed data. And similarly, the left skewed data would look just the opposite. It's a mirror image. There are a lot of values, there's a lot of lesser values, but with lower frequencies. The higher frequencies is on the higher side. So that's the left skewed data. All right. And we can also confirm this basically for the right skewed data, if we see, if we try to print the mean of the right skewed data, let's see what it is. It is 9.85, right? And median of the right skewed data is 6.6. So mean is greater than median, which means that mean is greater than median, which means that it is a which points to the fact that it's a right skewed data, right? And similarly for the left skewed data, it would be just the opposite. It would be just the opposite here. So we will do left skewed data, right? So the mean is 90, median is 93. So mean is less than median here, and hence it's a left skewed data. Okay. Now we come to the concept of kurtosis. So kurtosis is basically a measure of how fat or how thin the distribution is, right? So the distribution could be thin, the distribution could be flat, right? If it is thin, it has very sharp, uh, you know, uh, peak, right? So kurtosis is also known as the peakedness of the data, how sharp the peak of the data distribution is. So there are three types of kurtosis again, mesokurtic, where the normal kurtosis, it is the measure of the KPI, the measure is close to 3. The leptokurtic, which is a high kurtosis, and it means a sharp peak, right? So high kurtosis, which is greater than 3, and there is a platykurtic, which is a low kurtosis less than 3, right? We will now see examples of this as well. Again, I'm creating certain distributions. So we could obviously look at the kurtosis of the data we have created so far. For example, the symmetric data. The normal distribution that we had created has a kurtosis close to 3, so it's a very normally distributed. The right and the left skewed data both have kurtosis greater than 3, right? Which means that these have very sharp peaks. So we could actually look at that also, right? So if we look at this distribution here, we could clearly see that it is a sharp peak and then there is a sharp fall off, right? So hence it is a leptokurtic data with a higher kurtosis. However, I also am creating certain other distributions. So these are example distributions, okay? So of the leptokurtic and platykurtic data, and we will plot these and see. So leptokurtic data here, you could see that if we actually also print out the kurtosis of this, right, we will see it's a 6.3 kurtosis, which means that it's it has a sharp peak here, right, and it's leptokurtic data. So that is one example. Another one example is that of the platykurtic data, which we do not see any sharp peaks here at all, right? And that is why this type of distribution can be called platykurtic. And if we similarly look at the kurtosis value, see it is lesser than 3, so 1.7, right? So this is an example of a platykurtic data. So when we look at real world distributions, we should, in addition to main measures of central tendency and kurtosis, sorry, measure of central tendency and dispersion, we should also look at the skewness and kurtosis of the data also to get a complete picture. Hope this video was helpful. If you're liking this series of managerial statistics, please do like and subscribe to our channel and stay tuned for further videos. Thank you.